there are 5 problems in the test and 2 bonus problems.
5? Sounds kind of scary, actually.
This is the last big test we'll have. The other 2 will be shorter. But yeah, we'll take the whole period. You get 15 minutes per problem, which is roughly the same as you would get on a regular final. Question 1 is a Green's theorem problem. So 2 parts, just like the one in the second part of the past finals, where they ask you to do a line integral directly and also by Green's theorem. So
sure.
Problem 1 is going to be something like that. So I'm just going to describe a closed curve in R2 and say, do this line integral around the curve and also do it by a double integral using Green's theorem.
On R2?
In R2, yeah, the Cartesian axis, xy. Right, Green's theorem is 2-dimensional.
I know.
Right? So, yeah, of course it's going to be piecewise smooth, so you're going to have to break it up into several pieces, integrate along each curve, and add them all together for the direct way. The second problem is just computing a random surface integral over a vector curve, right? So that's maybe I should. So problem 1 has 2 parts. Do a line integral directly be the same integral by Green's theorem. A double integral. And problem 2 is going to be to compute a f dot ds integral, right? So I'm just going to give you a random vector field, describe a random surface, and I want you to compute this integral. Problem 3 is to compute
The curl?
a surface integral but over a scalar field. Right, so you're going to have to know how to do surface integrals over vector fields and scalar fields.
Okay.
Problem 4 is straight out of Calc 3, compute a triple integral.
Question. You're not going to try tricking us again, will you?
Come again?
You're not going to try to trick us with like a hard integral, right?
No, there are no real tricks here.
So no double angle theorem?
No what?
No double angle theorem?
It has trick in. Well, double angle theorem is not a trick. That's not a trick. Right.
Fine.
So for some
sine cube data.
solid key. Right. So I'm just going to describe a random solid. In fact, this guy has 2 parts.
Jhevon, is there a part B for question 3?
No, that was it.
Oh, okay.
I'm just going to tell you a surface and say compute a certain integral. Right. Same thing for this. Just compute an integral. Just doing that. Part 4 has 2 parts. I'm going to ask you to set up 2 of these integrals and then B, evaluate any one of them.
So set it up, meaning you can use whatever form you want to represent.
Yeah. Right, so I'm not going to force you to use cylindrical or force you to use spherical or force you to use rectangular. You choose whatever you want to set up, just make sure you do it right. And make sure you do it in such a way that you would be able to evaluate, right? Don't set up this crazy integral in rectangular coordinates if it's going to be super messy to compute it in part B, right? So I'm going to ask you to set up 2, so I'm going to describe 2 surfaces, and you're going to set up 2 triple integrals, but part B is only to evaluate any one of them.
Wait, so we need to do 4 integrals in total?
No, you're not doing an integral, you're setting it up.
So we set up 4 integrals, basically.
No, you set up 2 integrals,
But two
and
surfaces.
compute any one.
But two surfaces though.
Yeah.
So bounded between two surfaces?
No, I'm going to describe one surface here and another surface here, and say set up a triple integral for this one, set up a separate triple integral for this one.
Oh, okay.
So you set up two triple integrals for two different
I thought you
surfaces.
meant to do two different for the same one. Like
No,
okay.
no, it's for two
Yeah.
separate problems
Okay.
altogether, right? I'm going to describe two separate surfaces. I'm going to say set up the two separate solids. Set up the triple integral over these solids.
All right.
All right, so you're going to set up two triple integrals. And then B, just evaluate any one you feel like. Right? Whichever one's easier for you, just evaluate. Right? And you will have the freedom as to what coordinate system you want to set these up in. And problem 5. Is to compute an f dot yarn. But that probably won't look that big of a deal, but it's in 3 space. Right, so I'm going to give you some random curve floating in space, right? It's not going to be in just the xy plane. It's going to be in the R3, and I just want you to set up and do f dot d. That's going to be it. And that will be the exam, and you will have 50 minutes to do each of these problems. Yes?
Will they all have equal number of points?
No. Well, I believe each problem is worth 20 points, yeah. So the ones with 2 parts, I think I gave 10 for each.
The thing is, I feel like if you wait, so seven questions in total because there's 2 bonus.
Yeah, there are 2 bonus problems.
So 7 in total.
Right, but this is the actual test. This is what you should be able to do. 6 and 7 will be a Stokes theorem problem.
We haven't learned that yet.
I know. That's what's a bonus. Stokes theorem problem and a divergence theorem problem.
How much will they be worth?
I believe I made them 10 points each.
What?
Yeah, so it's possible to get 120 points on this exam.
And additional points will be transferred to the previous test or anything?
If you score more than 100, then I will transfer your grade to the next highest test, which I will probably wait on your 3rd test to do that, since the
Can you transfer all those? Can you transfer those to the quizzes?
No, no. Bonus points from quizzes go to quizzes. Bonus points from exams go to exams.
Okay.
I mean, the exams are the major chunk of your grade anyway. So.
The thing is, are you gonna make it like really difficult for us so it's possible? So it's only possible to barely finish all 5 within the allotted time, or are you making
No, I mean what's in the exam is pretty straightforward.
Okay.
I think one of the problems in the bonus is kind of messy computationally to work out. And in general, I don't like giving problems like that, but they do show up. And in one of the finals, I realized that one of the Stokes theorem problems was really messy to work out. So I chose a problem where that would be the case for problem 6. But this is just computationally. And conceptually, there's not going to be any curveballs or anything.
Okay.
One thing I will say is that I expect you guys to be flexible. So in the sense that don't always have one point of view, right? I'm not just going to give you if I give you a cone, it's not just going to be z squared equals x squared plus y squared, which is the cone you're used to seeing, right? I might flip a cone on its side, let it run along the x-axis instead of
But
the
they'll
z-axis.
all be centered at 0. The lowest be centered at the origin, right?
The vertex of the cone, yeah.
Okay.
I'm not going to be crazy, but I might throw it on a different axis so that when you're finding that normal vector, the 1 would have to be in some component other than the z component, right? So, I mean, other than that, there's really no tricks. Everything is pretty straightforward.
Okay, so it'll definitely be possible to complete all the questions within the allotted time.
Yeah. In my previous classes, I've had people complete all 7 in the allotted time. I mean, if you complete the 5 in the allotted time, you're pretty good because, like I said, on actual finals, you get roughly 15 minutes per problem, right? And with 5 problems, 15 minutes is the whole class period, right? So you do get 50 minutes for each problem.
For Stokes and divergence theorem, do we have to just show their formulas, or do we have to actually compute it?
I would expect you to compute it. I'm going to give you something else.
How far into Stokes and Divergence do we know? Just the formula and how to use it? Or
Yeah.
so this it's one formula and that's it?
Huh?
It's like one formula and that's it?
Each of them is one formula, yes.
Oh, okay. So we can just look at
Yeah.
formula.
It's just an equation. You know, like Green's theorem, it was just this equation that you just apply. They're sort of the same thing. Yeah, so that's what the test would look like. So, yeah, I guess now we can do some review problems. So, from the review sheet.
Homework first. A homework question?
Do you have a homework?
Yes, I do. I was able to finish it, but it's pretty long, so yeah.
We'll see.
I'm telling you it's long. Sure, 27?
Let's see. So this is a homework from what section?
13.7. 27?
13.7 and 27. Oh,
Good luck.
So it's one where you're going to have,
4 surfaces.
yeah, it's 4 surfaces. So it says evaluate the integral for the given vector field surface. In other words, find the flux, blah, blah, blah. S is going to be
It's pointing outward.
oh, yeah?
It's pointing outward.
Yeah, they said positive. Oh, no, sorry, positive is 1, 2. Okay, so do we know what this looks like?
Yeah.
So if you look at this guy, just think of this inequality, right? And write it as an equality. Right? This means you have z squared is equal to 1 minus y squared. In other words, y squared plus z squared equals 1. Right? Which is just a cylinder that's running along the x-axis.
No, wait.
Right? But you only have the top part because you take the positive radical. So remember, it's really only half a cylinder. But this is just telling you you'll take the top part. Right? And it's running between x is 0 and x is 2. Right? So here you actually have, as you said, 4 surfaces. There's the first one, S1, then there's S2, then the back would be S3, and the bottom would be S4.
That's the top part is because y squared plus z squared equal 1, right?
That's this one, the top part is this one. The surface Z equals the radical of 1 minus y squared. That's a cylinder. So remember that flux is the double integral over S of f ds. And in know that the double integral over S is just going to be the integral over S1 plus the integral over S2 plus the integral over S3 plus integral over S4. And so let's begin. Start with S1. How would you do it?
Normal vector.
Sure, has to have a normal vector. It's pointing straight out.
So 1, 0, 0.
N is 1, 0, 0. That's because you're thinking of S1 as a
Right.
function of what?
I'm thinking of y and z basically. F is equal to x, which is a function
Yeah,
of x.
this is x equals
To
2,
f.
right? So you take that to be f of y and z, right? It's just a constant plane, right? And so you know that the normal would be equal to, because it's outward pointing, 1 comma minus f y comma minus f z, but the partials of a constant is 0, and so you get 1, 0, 0. Right? And so we will have double integral over S1 is just double integral over d of x squared, y squared, z squared, dot 1, 0, 0, 8. All right, so you're just going to have the double integral of x squared be 8. But your x is a constant 2, so this is just the double integral of 4 d8. Right? Where your d is the region of projection in the yz plane, because it's a function of y and z. But that is just a circle of radius 1, right? A semicircle of radius 1. This is 4 times the area of semicircle of radius 1. I mean, you could go the long way and set it up with polar coordinates, but I don't
Same thing.
really want to do that. So this is 4 times pi over 2 times r squared. So S1 is 2 pi. All right? And notice for S3, just kill this one because it's pretty easy. It's also, the surface is x equals 0, and so your normal vector would be minus 1, 0, 0. And so your double integral over S3 would just be the double integral of x squared dA, which is just a double integral of 0 dA. So S3 is actually 0. It doesn't really affect anything. Next, let's do S2. And what's our surface for x2? This is z is equal to the radical of 1 minus y squared equals f of xy. Right? So here I would have normals pointing up. This implies my normal vector will be minus fx minus fy positive 1. So I take the partial of that with respect to x, I get 0. Take the partial with respect to y, what do I get? What's the partial of this with respect to y? It would be minus y over the radical of 1 minus y squared, but we take the negative of that, so right, so that's actually our normal. And so now the integral over s of f, the integral over s2 is just going to be the double integral over d of x squared, y squared, z squared, dot 0. Y over 1 minus y squared, z squared. So this is the double integral of y cubed over radical of 1 minus y squared plus, what, this was 1, plus z squared, but z was this, so this is just 1 minus y squared. So here we can set this up as, what's the setup here? my integral is a function of x and y, so my region of projection is in the xy plane. In the xy plane, I just have a rectangle.
Professor, I have a question. With respect to known vector, why did you do it? Why did you do it that way? Why did you do it as a function of x and y? Because really, it's another type of function. Because you have z is equal to z is with respect to y, but not with respect to x. X is its own thing.
What do you mean?
It's like how you parameterize a cylinder.
It's not a parameterization. I wouldn't do a parameterization. Remember, I always try to avoid that.
No, but I'm
Just because an x doesn't show up, it doesn't mean that it's not a function of x. I mean, you see things like that. A constant function, for example, right? If I say f of x equals 2, is that not a function of x because there's no x in it? No, right? It's just still this horizontal line 2.
No, I know that, but I'm saying that the x isn't gone. The x is equal to x, and x has its own boundaries. So I'm thinking maybe you should have done the partial with respect to x and then the partial with respect to y.
I did, but I take the partial with respect to x and y of the function, and my z defines my function, right? My surface here, I can explicitly define it in terms of z. I can say z equals some function. Whatever that is, that's f of x, y. And then I take the partial with respect to x and y of that function, right? My limits on x, don't worry about it, it comes back in my region of integration, right? This is telling me that my limits on x go from 0 to 2. I don't have to actually parameterize it to say that. It's already going to be given in my limits. Right? So you don't need to parameterize here. Right? So your z is, once you have it explicitly as something, that's a function of x and y. And you just call it that and run with it. Right? So this is our guy here, and so now we just have to set up this integral. So here our x goes from 0 to 2, y goes from -1 to 1 of y cubed over the radical of 1 minus y squared plus 1 minus y squared dy dx. Not technically, actually. If you take the integral from -1 to 1 of this guy, what kind of integral is that?
0. 0.
It is going to give you 0.
It's odd.
But it's odd, right? It's sort of funny, though, because it's actually an improper integral, right? Which is sort of weird. If you plug in 1 or -1, you actually get divided by 0. So technically, we have to do something like this, right? So like n goes to 1 of minus n up to n y cubed over 1 minus y squared y, or something like that. But basically it's an odd function on a balanced interval, so the limits are going to work out, right? Just trust me, it converges. Right? If you want to actually go through the whole process, you'll see it converges. And
do you need to prove that it converges though?
Yeah.
In the exam, if you give us, we have to prove that it converges?
Yeah, it'll converge.
Okay, I know it'll converge, but
it converges, and so we have odd function over balanced interval so this guy is equal to 0. But technically it's an improper integral, so you sort of have to at least just mention, you know, and so finally our integral over S2 would be equal to integral from 0 to 2, right? So remember, this guy goes to 0, when you actually take the integral on the inside. So now we just have to worry about those other guys. So this is just y minus y cubed over 3 between minus 1 and 1. So then this would be 1 minus a third minus minus 1 plus a third. So that's 2 minus 2/3, which is going to be, this is 6 over 3 minus 2 over 3, that's 4 over 3. So it's 8 over 3. Okay. And the last surface we didn't do was what? S4? This was also just a surface. This was actually z equals 0. So my n would be 0, 0, negative 1. And so the double integral over S4 would be equal to the double integral over d of x squared, y squared, z squared dot 0, 0, negative 1, 8. This is just the double integral over d of minus z squared d8, but my z is 0, so then this guy is just 0. Therefore, the integral over s is equal to, I erased the previous guys. Well, one of them is 8 over 3, that I know. What was the other one?
2 pi.
Was 2 pi?
Yeah, and that one's 0.
And the others are 0.
That's 0. Yeah.
Yeah, so that one you had 4 surfaces. I don't think I put one with 4 surfaces.
No, 2 is fine.
I'll let you guys know. But yeah, that one's just really long and tedious. Yeah,
With-
so
Okay, with the convergence thing, do we need to prove it? Like, if we know it's convergent, do we have to say, oh, it's convergent because of that, or?
no, you don't have to prove it. I wouldn't worry. Just like mention convergence. Right. Especially if it's like an odd function on a balanced interval. You sort of don't have to worry about it, but you know, technically if you want to be a good little mathematician, you should check things like that. Anyway, so I'm just going to run through a bunch of problems. I picked a random bunch from the finals, and then after that, if you guys still have questions about something else, I will go through those as well. So I'm just randomly picking problems here, so don't read too much into it. Just because I pick a problem that might have a cone in it, don't think the exam is going to have a cone on it or anything like that. I'm just picking questions that cover the same topics that will be covered on the test. And so for the list of problems that I want to do is all the problems from Spring 05 that were on the review sheet, as well as Fall 05 problem 7b and Spring 06 problem 7a. And then afterwards, we will open for questions. Okay. So. Okay, so this is a two-part problem. This is one of the Green's theorem ones. All right, so problem 1 on your test will be similar to this one. Okay, so R is a region. It is x plus 2y less than equal to 4, x greater than equal to 0, y greater than equal to 0. C is the boundary of R.
X squared.
counterclockwise oriented. It's positive orientation, and we want to evaluate the integral of sine x plus y squared to x plus 2y dy. Directly as a double integral. Okay, so like I said, problem 1 on your test is very similar to this. I'm just going to describe a region like that. Say C is its boundary curve, and then I'm going to ask you to compute some random line integral in 2 different ways. Okay, so first let's look at our region. What is that? Well, again, you start to look at the equations of these guys, right? So look at this, think of it as an equality, so it's x plus 2y equals 4. What kind of curve is that?
A line.
It's just a straight line, right? If you set y equals 0, you get x equals 4. If you set x equals 0, you get y equals 2. And so I have this guy. My x is greater than 0 and my y is greater than 0, which means it bounds this triangular region here. That is my region R, and I am oriented counterclockwise. So I have 3 curves here, C1, C2, C3. Right? This line here happens to be the line x plus 2y equals 4. And so now let's do it directly. So we're going to have to do it along each curve and then add them together, right? So C1, how do we do that? So in C1, we're going from the point 0, 0 to the point 4, 0. This is the point 0, 2. Right? So your x goes from 0 to 4. Right? So it's 0 plus 4t. Right? You start at 0, you have to add 4 to get to 4, so it's just 4t. Your y is constant at 0. Right? So it means your dx is 4 dt, your dy is 0 dt, and so your integral along C1, and of course t goes from 0 to 1. I'm using the standard parameterization here. And so this guy, right? So I'm just going to plug in my parameterization into that. The limits go from 0 to 1. My x is actually 4t, so it's sine of 4t. My y is 0, so the 0 squared, so it's just sine of 4t, times the dx, which is a 4. And then my y is 0, so this part is gone. So I just have this. Right? So then you find the antiderivative of that, which is going to be minus cosine 4t.
How do you get the boundary for t? 0 to 1?
So it's
Standard.
It's always
I use the standard formula for parameterizing line segments, and with that, it's always 0 to 1. Right? It's the initial plus, you figure out the difference to get to the final times t. And when you do that, it's always going to be 0 to 1. There are other ways to parameterize line segments, but with that standard formula, it's just a way to get into it. You know, you don't think about it, you just do it 0 to 1. So then you integrate that, you get that, and you plug in 1, you get minus cosine of 4, minus you plug in 0. Cosine of 0 is 1, so this is just minus 1. So here you just get minus cosine 4 plus 1. Now we're going to do C2. Now in C2, I'm going in that direction, so my x value starts at 4, it ends at 0.
Aren't you bringing the 4 for the cosine?
no, it cancels out already.
No, it'll cancel out,
Oh,
right?
yeah.
Yeah. If you differentiate this with the chain rule, you will get the 4.
So it's something general because you.
Yeah, if you differentiate, you'd use the chain rule.
Yeah.
Now my x goes from 4, that's my initial point, and it ends up at 0. So you put the initial, x is 4, what do you have to do to get to 0? You have to subtract
Subtract
4. So it's minus 4 and attach a t to it. My y starts at 0 and it goes up to 2. So 0 is the initial point, and then to get to 2 I have to add 2.
Yeah.
So just plus 2t. And then my t goes from 0 to 1. Right? And so now I can find my dx, my dy, and so my integral along C2 is just going to be the integral from 0 to 1. And again, I'm going to plug in everything. So this is sine of 4 minus 4t plus y squared times dx, which is minus 4, plus 2 times y times dy, which is 2. So let's expand this. This is minus 4 sine 4 minus 4t minus 16t squared plus 9t dt. And so this would be what? The integral of this would be cosine of 4 minus 4t still be a minus. And this would be minus 16 over 3 t cubed plus 4t squared. So if I plug in 1, I get cosine of 0, which is minus 1. Plug in 1 here, I get minus 16 over 3. 1 here plus 4. Minus, when I plug in 0, I would get minus cosine 4, and then everything else is 0. So this part I get minus 1, minus 16 over 3, plus 4, plus cosine 4. And then finally, the last curve, C3. In C3, my x value remains constant at 0. So x is 0, dx is 0. My y value starts at 2, but then decreases to 0. So I put the initial point, starts here. What do I have to add or subtract to get to 0? I have to subtract 2, attach a t to that. 0 to 1. My dy would be minus 2 dt, and so integral along C3 equal to integral from 0 to 1 of, plug in 0 for x, sine of 0 is 0, so forget it, y squared would be 2 minus 2t squared times dx, which is 0, so that part doesn't matter, and then plus 2 times y times negative 2. So then this is minus 8t plus 4t squared. It's minus 8 plus 4 minus 4. This implies integral on c is just going to be minus cosine 4 plus 1 minus 1 minus 16 over 3 plus 4 plus cosine 4 minus 4. These die, 1's die, cosines die, and we're left with minus 16. Any questions?
Greaser is a lot easier.
Yeah, but they always ask you to do both ways, so. Let me get rid of this part. I'm going to do part B. So it's the same region, but now we're going to use it do it using Green's theorem. We know that the integral along C of P dx plus Q dy is equal to, this is by Green's theorem, is equal to the double integral over d of qx minus py dA. It's positively oriented because we're counterclockwise, so I keep a plus sign here. And here my p is actually equal to this guy, sine x plus y squared. My q is equal to this guy. And so this means py is 2y, qx is 0, and so my line integral along C is actually equal to the double integral over d of 0 minus 2y. So if I compute this single double integral, it's the same as doing all these three curves and adding them together. So now D is the region of integration. Well, technically it's really R, right? And so I can set this up in any way I want. I would prefer to solve for x because then I avoid fractions. And so I would let x go between functions, y go between constants. My y would go between 0 and 2. My x would go from the function x equals 0 up to the function x equals this. So this would be minus 2xy between 0 and 4 minus 2y. Plug in this for x, I would get minus 0, that's gone, so it's just dy. This will be minus 8y plus y squared minus 4y squared plus 4 over 3. Cubed. Plug in 2 here, I would get minus 16, plus plug in 2 here, I would get 8. 8 times 4 is 32. So 16 is actually 64 over 3. So this is that right? There's 48. Right? And if you take minus 48 plus 32, you get minus 16.
So you're right.
So, yeah. So the good thing about these problems is that you can always know if you're right or wrong. Right? Your answer should match up. And in general, you're going to be given a Green's theorem, a Stokes theorem, and a divergence theorem, and you have to pick 2 out of the 3 in the final. In general, I think the Stokes theorem problem tends to be harder, so if you know Green's theorem and divergence theorem, you should be in good shape. But it's good to know everything, of course.
Could you just tell me how you got the limits?
So this is my region. I want to set up the double integral. So you choose who you want to go between constants, who you want to go between functions. Right? The constants go on the outside, the functions go on the inside. So it means I have to solve for one variable in terms of another. I chose to solve for x, because if I solve for the y, I get a half. I don't like fractions, so I avoid fractions. So I wrote x as a function of y. And so I want my x to go between functions. Right? So if x is going between functions, it's left up to right. Right? Bottom to top becomes left to right. The left function is x equals 0. The right function is that. So I put 0 to this. And then if I look at my y, I only care about the constant bounds. The constant bound here is 0. The constant bound here is 2. So it's just 0 to 2. S is the part of the plane Z equals 2 minus x minus y. Or its options. C, the boundary of S. Clockwise. F is the vector field x, y, x, y, z. Find F dot. So we know this is a plane, 2x plus y plus z equals 2. And if y and z equals 0, x equals 1, y would be 2, z equals 2. That's our plane. If you're looking from above, it's counterclockwise oriented. So it means your arrows are going around that. So my boundary curve C has 3 parts. And yeah, I'm going to find f dot dr. I have to actually do it for each curve. So if I do C1, this is going from 1, 0, 0 to 0 to 0. This is 0, 0, 2. So look at my x coordinates. My r is going to be a straight line. X goes from 1 to 0, so it's 1 minus t. Y goes from 0 to 2, so it's 2t. Z is remaining constant at 0. T goes from 0 to 1. Right? So my steps here is to figure out what I'm going to do. Find r, find dr, find f of rt, dot product integrate. Right? That's the set of steps we take here. F of rt just means I go to my function f and I plug in this parameterization. So my x I'm going to replace with 1 minus t. My y I'm going to replace with 2t. And then this is x, y, z. My z is 0, so it kills everyone. That's this guy. And so the integral along C1 is just the integral from 0 to 1 by dot product these. So it's this times that, t minus 1, this times that, 4t, this times that, 0. On to C2. In C2, my x is constant at 0. So my RT just has 0 x component. Y goes from 2 to 0, so this is 2 minus 2t. And my z goes from 0 to 2. So this is 2t. T goes from 0 to 1. So find r, find dr, find f of rt, dot product integrate. Here my x is 0, my y is 2 minus 2t, and then x, y, z would be 0 because x is 0.
We don't need to say the boundaries from 0 to 1 each time.
Technically, but if you know it, you should know. I would say write it down. Yes. And And so the integral along C2 is integral from 0 to 1, 0 times 0. This times this is minus 2, so it's minus 4, plus 4t. 0 times that is 0, so it's just this guy. And we would have minus 4t plus 2t squared minus 4 plus 2 minus 2. And now C3. So in C3, look at my x-coordinates. It goes from 0 to 1. So my r of t is just t. My y value is constant at 0, so y value is just 0. My z value goes from 2 and decreases to 0, so it's 2 minus 2t. So find r, find dr, find f of rt, dot product integral. So replace x with t, replace my y with 0, replace my x, y, z would be 0. And so the integral on C3 is just the integral between 0 and 1 of t, dt, which is just a half. Therefore, the integral on C is just going to be the sum of all of these, which for C1 I got 3 over 2. For C2 I got minus 2 plus a half. So we did all that work for nothing. And any questions? A bonus, B. Let's actually do this using Stokes' theorem. Now Stokes' theorem is like a higher dimensional version of Green's theorem. So remember in Green's theorem we said if we're in R2, then if you take a line integral around the boundary, it's equal to a double integral over the region that it bounds, right? In Stokes' theorem it's exactly the same thing. In fact, where you know that the f dot dr integral around the boundary is going to be equal to a certain surface integral around the surface itself. Right? And the equation in Stokes' theorem, provided that several assumptions are fulfilled, is the following. Right? The f dot dr integral, in general, is equal to the surface integral over the S, right? Where C is the boundary curve. Hence, it's a closed curve in space of this surface. Then this integral is actually going to be equal to curl f dot ds. Right? That's the equation that Stokes' theorem says.
Wait, so it's curl f and dot ds?
Yeah.
Okay.
So it's the ds integral over a vector field, but the vector field that you're taking is the curl. Right? So in Stokes' theorem, that would be the equation that you'd write down and you just apply it here. So instead of doing it this way, where we have to do 3 separate lines and add them together, we're going to do this single double integral. This one double integral.
So it really be curl of f dot, you know, vector.
Yeah, curl, right. That's going to be the double integral over d of curl f dot n dA. Right? And of course it's oriented, so you have to know where your normal vector is pointing. Counterclockwise is positive orientation, so it points out. Right? Now we'll get into the theory more in class, but for now this is all you really need to know. Right? Know this equation and you'll be able to compute it. And you know counterclockwise just means it's pointing out or up. So now you would have that. So let's actually do that. We know our f is this guy, which means our curl f. Remember how to compute the curl?
Yep.
Right, do that basis then, right? I, j, k, partial with respect to x, partial with respect to y, partial with respect to z, of x, y, x, y, z. So that is xz minus 0. This is yz minus 0, so it's minus yz, 0, 0. That's going to be my curl. And so my f dot dr, let's find the normal vector. My normal vector I'm going to take to be minus fx minus fy positive 1, because I know my z in the beginning I was given z explicitly, so I can compute the normal vector that way, just make sure it's pointing up. Right? And so this means that my normal vector is actually just, take the partial of this with respect to x, you get -2, take the negative of that, you get 2. Partial with respect to y is -1, negative of that is +1, and of course 1. So this is my normal vector. Now if I dot product it with this and integrate over this the region of projection, which is going to be in the xy plane, I will actually, should get 0. Dot product this with this, so it's 2 times this, 2xz, 1 times this, minus yz, 0. Right? But of course this dA is in x and y, so I have to replace my z with the function. Set up this region. Choose who goes between functions and constants, right? So I know in the xy plane, I look like this, where my x goes from 1, my y would go to 2. This is my region here. How do I know what equation this guy is?
Make it up.
Right, you could do y equals m equals b, but it's actually longer. Just use the original equation of the plane, right? This is the intersection of this surface in the xy plane. Just make z equals 0, that gives you the line right away. And so you get y equals 2 minus 2x. And so here, my x goes from 0 to 1, y goes from 0 to 2 minus 2x, 4x minus 4x squared minus 2y plus y squared. So we integrate with respect to y. And so this will be 4x times this, so it's 8x minus 8x squared. 4x squared times this, so it's minus 8x squared plus 8x cubed, y squared plus a third y cubed. So now you integrate, this would be 4x squared minus 8 over 3x cubed minus 8 over 3x cubed plus 2x to the fourth minus
No.
It's 2. So this
Yeah.
would be 6, and that would be positive, right? Minus, this would be 2 over 2x to the 4th. And 3 times 4 is 12.
It's 2.
Over 2, so this is 24. It would also be a positive, right?
No, I wouldn't agree.
So you bring the 4 down, right? 4 into 24 goes 6 times. This will become a cube. You would multiply
By
by
the negative.
negative 2. So you would get, oh, it was positive before.
Yeah.
Okay, so it's negative. And so now you just plug in 1. If I plug in 1, I get 4 minus 8 over 3 minus 8 over 3
0. And then 0, 0.
plus 2,
0
and then zeros. If I plug in zeros, I would get,
2 over 6.
if I plug in 0, I get 2 cubed over 6.
Oh, yeah.
Minus 2 to the 4th over 24.
Over 6.
So this is 6 minus
16 over 24.
16 over 3 minus, this I can reduce, right? 2 into this goes 4, 2 into that goes 3, plus this I can also reduce. 8 into that goes 2, 8 into that goes 3.
Yeah, 24.
And so this is 6 over 6 is actually 18 over 3. So 18 minus 16 is 2 minus 4 plus, so that's
2 over 3 plus 2 over 3. Okay, yeah.
Alright, so it's just knowing what equation to apply. And like I said, sometimes the Stokes theorem problems, they get a little messy with the arithmetic and the algebra that you have to do. So just be aware of that.
Is it sometimes or occasionally?
Come again?
Is it sometimes or occasionally?
What do you mean sometimes?
Sometimes it's less it's less often than occasionally.
Occasionally what? Like it's a messy
Yeah.
problem? I would say most of the time.
Most of the time. Okay.
Yeah.
Okay.
I mean, if you look at the past finals and you do the Stokes theorem parts, you realize that
They're
like
always
3 out of
messy.
4
Yeah.
times it's going to be rough. All right, the Green's theorem and Divergence theorem is usually the easier ones. So they say T is a solid, x squared plus y squared less than equal to 1 for z between 0 and 1. So it's just a cylinder of height 1. This is boundary surface at T. And so it includes all sides. The normals are outward pointing. In other words, it's a positive orientation. And my W is a vector field y squared, x squared, sine squared, z. So instead of big F, they call it W. It doesn't matter. It's just a dumb.
Yes, sir. Will you be as nice as them?
Come again?
Will you be as nice as the final?
What do you mean?
They actually explicitly said it includes top, bottom, and side.
No.
You're not going to say
I'd
that?
probably say something like this. Boundary surface, right? If I say boundary, I expect you to know it completely surrounds it.
But isn't the final? Okay, sorry.
But this is a problem similar to what I would give. It's pretty comparable to the exam. The only trick I would try to throw into this is just give you a cylinder that's on its side. So I might say like y squared plus z squared.
Okay, yeah.
Or something like that.
Yeah, but you'll
You know,
never
Otherwise,
away from the origin, right? You'll never move away from the origin. If you move away from the origin,
I
it's
believe
really complicated.
I also put, there was a question, something like, it was a cylinder, and I actually sliced it with a plane, so it's like the slanted part. And yeah, so it was, I think it was something. Yeah, so there's one flat part, but then there's one slanted part. And then the side of the cylinder. This one is just straight.
Wait, so that's what you'll include in our exam?
Again?
So that's what, we should expect that on our exam, or you did that?
Yeah, expect something like that.
Oh.
But this one is just a straightforward cylinder, flat top, flat bottom. And I have outward pointing normals. So let's compute the surface integral over the vector field W. So of course you remember that this is equal to the double integral over d of f w dot the normal vector dA, right? So now we're just going to have to find the normal vector for each surface. So let's call this surface here S1, this guy here S2, this guy here S3. Okay, so let's do S1. Add them together. So normal vector is pointing straight up. This is just the surface z equals 1, so my normal vector is 0, 0, 1, right? If you can't see that right away, it's fine. Just remember you'd use minus fx, minus fy, positive 1, where your f is just a constant function, so the partials are 0 in both cases. And so now we can say our double integral over S1 is going to be equal to double integral over d of my w dot n. Only the last component is a 1, so it just gives me this guy. Sine squared pi z dA. However, my z is 1. So I just plug in 1. Sine squared pi dA. Okay, so how do we integrate that?
Half angle.
Half angle?
Double angle theorem. You could, one.
What do you think?
Wait, that's a constant, isn't it?
It's a constant. It's 0. Sine of pi is 0. Right? You guys are double angle theorem. Ha! Jhevon said not to forget this. I totally remember it. No, it's 0. Okay. S2. Okay, so now the problem with S2 is your normal vector is pointing straight out horizontally. It doesn't point up or down, right? Which means this guy is not going to work, right? Not unless you like slice the cylinder in half and do left and right. It's too much work to me. I just parameterize it, right? Right, so I'm going to write this cylinder as R of uv. What would I make x and y?
Well, x is going to be cosine. Actually, yeah, cosine.
Cosine u,
Sine u, and then
sine
b.
u, and z just be itself. My u, it's a full circle, so it's 0 to 2 pi, and my v is following the z, so that's just 0 to 1. And that's, so you cross it, right?
Yeah, generally.
Find the partials and then the cross, right? So it's r little u, this is minus sine u, cosine of u, 0, r sub v, and so on, normal. Remember, you just take the cross product of that, so it's cosine minus sine, but you take the negative, and that's 0, right? And if you check in the first octant, your cosine would be positive, so it's telling you you're pointing out in the positive x direction, so we know this is the right normal vector. You don't have to take your standard. So that's the normal vector we want, and so now the double integral over S2 just going to be the integral over d of this dot product with my w. Right? So let me actually write this out, because you're going to have to plug in the parameterization into that. So here you have y squared, but your y is sine. So this is actually sine squared u, cosine squared u, and sine squared pi v. The dot product with cosine u, sine u, 0.
Question.
Yes.
Question. If the cylinder was pointed this way, instead of pointed in this direction, then we could find the normal vectors on the two ends of the plane by considering the directions pointing as positive and.
Yeah, you mean like if the cylinder is like on its side, like
Yeah,
this?
yeah. Then we
Yeah,
should-
then a normal vector here would be pointing up, but the normal vector here would be pointing down, right?
So we've covered that anyway. But I'm checking about the two ends of it. Can I consider one end positive and the other negative, or no? Because it will be pointing in the horizontal.
This end?
Yeah.
Yeah, one end is just positive, so you just let this be 1, 0, 0. And then the other end would
Would
be
be negative.
0, 0,
Well, negative.
negative 1, 0, 0.
Okay. Okay.
Yeah. And of course, if I only gave you the top half of the cylinder, then you wouldn't parameterize, you would just
Yeah.
use the whole top or bottom half. That can work. So anyway, we have this, and so this is sine squared times cosine plus cosine squared times sine, and then 0. And my dA is just du dv, or I can put dv du. V goes from 0 to 1, this goes from 0 to 2 pi. So this is all a constant. Integrate with respect to v, I just get all this times v. Plug in 1 and plug in 0, just get back the same thing. So this integral would just be sine squared u cosine u plus cosine squared u sine u du. And so the hard way to integrate this is trig substitution, but you just realize that this is not trig u substitution. Right? So in the first one, you let u equals sine, your du would be cosine. T equals sine, your dt would be cosine. And you just integrate that to sine cubed over 3. Here, similarly, if you let u equals cosine, your du would, t equals cosine, your dt would be minus sine. And so you end up with this.
And what's that hard?
And so if you plug in 2 pi or 0 into sine, you get 0 both times, so forget that. Plug in 2 pi into cosine. Cosine of 2 pi is 1. So this is minus 1/3 minus But in 0 into cosine, you also get 1.
How is that hard?
Come again?
You said the hard way is doing this.
The hard way is doing what?
You said the hard way is doing U sub. So
Yeah, but I actually didn't write it out. I didn't write out the substitution.
oh, okay.
The hard way would be to like, you go in a corner and t equals this. I mean, at this point, I expect you to just see that this is that. If you don't see it, then the hard way would be actually to figure out, okay, your substitution.
Oh, okay.
And that was S2. So S1 was 0, S2 is also 0. What about S3? S3 is also going to be equal to 0. Yeah, you can see right away because Z is going to be 0 and everything. So here your Z is 0, your normal vector is just 0, 0, negative 1. And so your double integral over S3 is just going to be equal to the double integral of 0 is going to kill this, and 0 is going to kill that, and then you're going to have negative of this. So it's minus sine squared of 0, because I'm plugging in Z equals 0. But sine of 0 is 0, so this is just 0 as well. And therefore, the double integral over S is going to be equal to 0. 0 plus 0 plus 0. This one. And again, as a bonus, we're going to show you how to do this by divergence theorem. Let's do part B. So divergence theorem is, again, like Green's theorem and Stokes theorem, but it takes it even to a higher dimension. Here, your boundary is not a curve, your boundary are surfaces, right? Once you have a solid bounded by a surface, then you can compute the flux over all these surfaces by doing a triple integral over the solid itself. And the equation is the following. The double integral of double f dot ds, right? The double surface integral over a vector field is going to be equal to the triple integral over the solid of the divergence of f dv. So that's why I had to teach you about curl and divergence, because you use them in Stokes theorem and divergence theorem. And here, S is the boundary surface of E. Right? So you're relating a line integral over the boundary of a surface to the surface itself, some scalar integral over that. That's basically the underlying theme between Green's theorem, Stokes theorem, and divergence theorem. So some line integral on the boundary is equivalent to a scalar integral over the thing that the boundary encompasses. So now our boundary is actually a cylinder, so we can set up our limits like that pretty nicely. That would be cylindrical coordinates, but then first take the divergence of f, which in this case is w. So here, divergence of w is equal to, remember this is a scalar, it's the partial of each. So the partial with respect to x of y is 0, plus the partial with respect to y of x squared is 0, plus the partial with respect to z of sine squared pi z is going to be 2 sine pi z times cosine pi z times pi by the chain rule. So this is actually sine of 2 pi z times pi. And so I believe the solid was called T of the divergence dV. And so now I'm going to switch to cylindrical.
Actually, what happened to your sine squared?
I differentiate it. Right? This is replaced by the divergence.
No, but in divergence, you multiply the differential with the differential function,
I
right?
dot product the differential.
Yeah, and so your sine squared is gone. I mean, you
I
dot
have,
product
to
it.
I have to take the derivative of the sine.
Yeah.
Yeah. Take derivative of sine squared chain rule. You have to bring the power down, subtract 1 from the power.
Oh, yeah.
Multiply by the derivative of the inside.
Okay.
Okay, so now
Oh,
if I set up this solid, I can let theta goes from 0 to 2 pi, r goes from 0 to 1, z would go from 0 to 1 of pi sine 2 pi z r dz dr. So integrate this with respect to z, and we would get what? Integral of sine is minus cosine divided by 2 pi. Now if you plug in 1 here, you get cosine of 2 pi. So this is just minus a half times cosine of 2 pi, which is 1, minus a half times, plug in 0 here, you get cosine of 0, which is also 1.
so the answer is 0.
Well, that's just a double integral of 0.
Which is 0. Okay. That's easy.
I'm still a little confused. When you did that, what happened to the cosine? Oh, wait, no. I'm still a little confused. What happened to the cosine?
I use the trig identity. We know that 2 sine x cosine x is equal to sine 2x. I just used it to simplify. I mean, otherwise you could put this here, then you just integrate it using a u substitution.
And then-
Right? Let u be sine, your du be cosine. You get the same.
Alright.
I don't know if you guys want to take a break or want to continue.
5 minute break?
Huh?
5 minute break?
Okay, can take a break. Okay, sorry. We're moving on to
Can we do one scalar, a surface integral in a scalar field?
that is one of the problems we're going to do.
Okay, good.
The one I'm going to do now is one of the Cal 3 problems that showed up on a final.
Yeah,
They just asked you to set up and evaluate a triple integral.
yeah, I just did
And
that.
I'll probably talk about something like what I would give you on
It'll be harder, or
the exam.
will it be harder than what they gave us, or easier?
It'll be harder than this one.
All right.
Use a solid above. So everything's x squared plus y squared. Below. Equals 2. Find the triple integral over t. X squared plus y squared. Yeah, so what they do here, I would actually do it twice, right? I'm going to ask you two different things. I'm going to say there's a t1, and then there's a t2. Set up this integral, and then part B is just
They
about
did that for another problem, actually.
Sorry, part B was what?
They did,
Yeah, I know.
yeah.
I don't want to go through two calcs in
I'm sorry, part B, you said part B?
No, continue.
Yeah. Come again?
So you said part B was going to be what?
On the test, I'm actually going to ask you to set up two integrals.
Okay.
And then part B would be to evaluate any one of them.
spherical.
Was this
Oh,
supposed
so
to be a
very-
giveaway
okay,
problem?
Yeah.
Wait, was this supposed to be a giveaway problem?
Well, it is a top 3 problem. It's just you don't need any 392 for this.
You don't need to draw that.
Well, you should draw it just in case.
Yeah. So what kind of solid are we looking at?
It's actually a paraboloid.
Paraboloid.
Yeah, with a surface cutting in the top.
Alright, so it's this, and you're slicing with z equals 2. Right, so this is z equals 2, this surface is z equals x squared plus y squared. And the region of projection would just be a circle. What would be the equation of this circle?
Well, it'll be.
The
Well,
radius would be
wait,
2.
what?
The radius would be 2.
Right, z equals this, z equals that, they
You want me to
intersect, so you just
parameterize
plug in
this
z
or-
equals 2, right? So it's just x squared plus
Y
y
squared
squared equals 2. So in a circle center at the origin radius radical 2. Okay, so how would we actually set this guy up? I would use cylindrical, yes, right? My region is a circle, moreover, x squared plus y squared is something nice, right? So,
Square.
So, look at your region of projection. This is just going to be 0 to 2 pi. This is the angles, 0 to radical 2. This is the radius. My z would go from what to what?
0 to 2.
R squared
No.
to 2.
X squared
Right?
plus Y
Bottom
squared.
surface to top surface, right? This guy here is the bottom surface.
R squared to 2.
This guy here is the top surface. Right? The innermost integral of a triple integral is the surfaces. So this would be r squared
R d
up to 2
z
of this function, which is just r squared,
R squared
times r d z d.
Okay. You could. Oh,
So
yeah.
that would be the setup, and that would be like part 1, right, to do this twice. And then in part 2, I'm going to ask you to evaluate it. So this is just r cubed z r squared 2.
So it'll be like the other problem then.
Okay. This is 2r cubed minus r to the 5th. This is 1/2 r to the 4th minus 1/6 r to the 6th. Right, the d theta is going to contribute a 2 pi. Here, if you plug in radical 2 into this,
You
right,
get 2.
the trick is you can think of this as r squared squared. This you can think of as r squared cubed. Alright, so if you square radical 2, you just get 2. So this is 2 squared, and that would just be 4 minus 2 cubed is 8. So it's 2 pi times 2 minus 4 over 3. Okay, so this is 6 over 3, right? Minus 4 over 3 gives me 2 over 3. So this gives me 4 pi over 3.
So in terms of difficulty, the question that we should expect in our exam is similar to the other problem that was given to us. The way
Yeah,
you just
I
divided
mean-
both.
You can practice this. I might give you something like I take a sphere,
Okay.
but instead of intersecting a sphere with a paraboloid, I might give you like a sphere with a cone. And then I might make the solid this region under here, or only that region above here, or
I-
something like put the cone on the side. and then you get this here. Right? Something like that.
I
Right?
kind
So
of doubt with the cone, like,
the setup would actually be the same as if it was something like that, except the difference is your phi, your angle phi would be different.
yeah.
Right? So they might look radically different, but the only difference between this and that is the phi that you would choose. Right? So things like that, I want you to be flexible to know how to tweak something to get a different surface. Well, probably something like
A question.
that. Yes.
Phi only goes from 0 to pi. It never gets any further or less. Oh, it never gets any further than pi, and never any less than 0.
Right.
Okay, because it's twisting.
Yeah.
Okay.
One of those. Yeah, this will basically be a problem. I'm going to describe a surface and say set up this triple integral.
Okay.
And you set it up, and then in part 2 I'm going to ask you to actually just work it out. Right? So I'm going to ask you to set up 2 and then you evaluate the position. And there is actually a problem that is pretty much like that on a final, I believe, where it asks you to set up 2 triple integrals and evaluate 1. So you can look into that one. The last problem is spring 06. Six, seven. So S is given by the surface.
What are you doing?
Evaluate double integral of S of Z squared ds.
That's it?
That's it.
Oh,
A problem on the exam will just be that. So a problem is just going to be evaluate f dot ds, and then there's going to be another integral to evaluate this ds.
okay.
And the difference between this is, right, remember that this would be equal to the magnitude of the normal vector.
Yeah.
Right? So it's not a dot product now. Now you take the magnitude, you just multiply.
It's reminiscent of the original line integral that we learned about.
So let's do it. This guy is actually, again, a cylinder.
So we can like expect it won't be cylinder or any easy object like that in our exam.
I mean, the objects themselves would be simple, but I might do stuff like slice things
In
in a
half.
slant way or stuff like that. Also be careful when I describe something to be like the boundary of a solid as opposed to the surface itself. Right? Like for here, you should realize that S does not include the top and bottom. It's just the skin. Right? Otherwise, I would say S is the boundary of this cylinder, in which case, you know, you have to complete all surfaces that surround it. Right? Yeah, so now I only care about one surface, and that's this here, my S, my normal vector point out like that. So,
Average size.
I would parameterize it. can parameterize it by, I think we did something like this before. So this would just be cosine u sine u, and my u go from 0 to 2 pi, and v 0 to 3, equals 0 to 3. Okay, so now evaluate our u. V. So your n is just going to be the cross product. That's cosine sine 0. Doesn't matter which direction it's pointing because I'm taking the magnitude. So it's the radical of each component squared.
There's 1.
It's just 1. And so my double integral over s of z squared ds is just going to be my double integral over d of z squared times 1 dh.
Yeah, so we definitely can expect this. It's
And
right
so
here.
now my z, remember, is just v. Just v squared. And my dA is just d, whichever d, v, du. And so my v goes from 0 to 3. This goes from 0 to 2 pi. And so this is just v cubed over 3. 3 to this is just 9 minus 0. This will just be 18.
Okay, yes, this is much too easy for our exam. I mean, a 1 gone.
Can you follow me with the camera? My cameraman bailed on me. Okay. And that's basically it. What we covered so far covers the same material that will be on the test, right? So like I said, there's going to be a Green's theorem 1, and there's going to be, you have to compute the f dot des integral, then the f ds integral, regular triple integral, and
Volume. Oh, yeah.
which is the triple integral.
Stokes and Divergence.
And then Stokes and Divergence theorem that I gave you examples of, right? It's just knowing those two equations and applying them.
Question, will Stokes and Divergence theorem be a part of another?
It's not officially a part of the test, right?
No, but I mean, will the question relate to another question that we had before? So we can check our work.
Using Stokes theorem or using.
Yeah.
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 something like
So
that.
we check
So
our work.
I'll actually do something in the test, and then I'll probably actually verify your answer. using
Yeah.
it.
Okay. Good. Okay. So that
So
way we,
you'll know if you're right or wrong.
that's nice. No, you're kind of horrible. You hear like 10 minutes left.
Yeah. You get two different answers, like, no! Which one's wrong? Okay, just try to redo the easier one. Yeah, I mean, I've seen people, like, they do both of them and they get the wrong answer, and they just like scratch it out and put the answer in the other one. I notice these things. Don't think I just look at the answer and give you all the points. No.
Did you get more points though?
No.
Really?
I'd be like, I saw what you did here.
Professor, you need to change actually, but we're almost done.
Oh, well, we're almost done.
Yeah.
Is there any questions? Okay, I guess that's it. So I gave you the list of what I would
Okay.
give you in the test,
There,
and
will
that's
there be
it.
triggered? There will be triggered entities, basically.
Yeah, yeah. There's
Okay. Okay, so I'm just memorizing again.
Just practice the review and prepare for things like that, and prepare for things like that. So anything you think of too simple, like this cylinder, just think of ways to make it more complicated. Slice it this way instead, and see if you could still do the problem.
Yeah.
Right?
Do
So-
three cuts in it. 3 cuts. So you.
I wouldn't go as far, but yeah. Or like just turn the cylinder on its side, you know, something like that. And
Or off
see
the
if-
origin to make it
Yeah.
almost insane.
So every time you do a problem, just think, well, if you were to twist it or do something, could I still do the problem? Would I get lost?
Yeah, but the thing is,
I'm gonna do things like that.
for example, my chemistry teacher, he occasionally gave us problems that were off the origin, and they were insane. I mean, seriously, they were, but
Yeah,
They're not possible.
I'd still keep things like centered at their origin. I'm not gonna go that crazy.
it's
That's
not
it.
impossible though. It's of course it's not possible.
No, it's not impossible.
Yeah, but it's a lot more difficult.
Computationally messy.
Much messier. 1 plus sine squared. I mean, the 1 plus sine theta as one of your limits of integration.
Yeah.